Okay, I think we'll make a start. Today's lecture is going to be about titanium and its alloys. And I pointed out to you in the last lecture that titanium has a very high melting temperature, 1670 degrees centigrade. That's higher than that of iron. It's about 1550 degrees centigrade. It has a low density of the order of 4.5 grams per centimeter cubed. And therefore it isn't surprising that a vast majority of titanium is used in the aerospace industries, so aircraft and spacecraft and so forth. But nevertheless, it is surprising that the use of titanium is restricted to temperatures less than 400 degrees centigrade. So given such a high melting temperature, higher than that of nickel, for example, you use nickel-based superalloys in environments as hot as 1400 degrees centigrade. But titanium is restricted to temperatures below about 400 degrees centigrade. So if you look at the distribution of materials in a typical aircraft engine, you can see that titanium does not make it into the hot zone. Okay, the hot zone is really here, where the temperatures can be of the order of 1400 degrees centigrade. So there is a burn line effectively, where we restrict the use of titanium to temperatures less than 400 degrees centigrade. Any ideas why? They will catch fire. And the biggest problem arises when titanium rubs against another metal. That's when it catches fire. And the fire can be over in milliseconds. Okay? You can leave the rest of the engine empty. So it's a really hot fire.
What is it about titanium that makes that happen to it as opposed to various other metals?
Yeah. So it's got a protective oxide film, which is like aluminium. And like aluminium, it has a very, very large enthalpy change when you oxidize it. So once you get the reaction started, and that's the critical thing, it's very hard to stop it. Okay? This is a consequence of a titanium fire in an aircraft engine, and you can see all these blades have basically disappeared. Okay? And this can happen in a very, very short period of time. So this is the reason why we don't use titanium beyond about 400 degrees centigrade, because if a bit of titanium breaks and rubs against another piece of metal, we will have serious consequences in an aircraft engine. Yeah.
How is it cast? I mean, most metal processing involves heating up to a pliable temperature or heating to a liquid and then casting it.
Yeah.
So how do you cast something that burns above 400 degrees? Doesn't it?
Yeah. So it doesn't. I mean, if you take a piece of titanium, if you heat it, even 1000 degrees, it won't burn. It's this rubbing action which destroys the passive layer, and then problems.
So it'll be a passive layer even on the molten metal.
And you know, the other problem would be if you made it into a fine powder when you have a lot of surface per unit volume. That would also be dangerous. But you can certainly cast it, no problems at all, within reason. Okay? So these, for example, are the largest blades that you have in an aircraft engine, and they're made by casting, rolling, etc., without any difficulty. Okay, now the crystal structure of pure titanium at ambient temperature is hexagonal close-back, and you recall that hexagonal close-back means the stacking of layers in AB sequence. Okay, so these are the close-back layers of atoms in AB sequence, and you can see that this is your hexagonal unit cell with an angle of 120 degrees here. This is the view from the top. And the C over A ratio, that means the C lattice parameter, A lattice parameter, is almost ideal. You know, if you look at the closed packing of spheres, then the C over A ratio will be 1.633, ideally. Okay. This just goes to show that atoms don't behave exactly like spheres, but it's not far off ideal. So it's hexagonal close packed at room temperature. And normally we say that, you know, there are only 3 slip systems. That means the slip plane is the basal plane, and slip directions are within the 3 close-back directions within the basal plane, right? But in fact, titanium can also slip on this prism plane here, okay, because that also contains this closed back direction, which is the direction of slip, and on the pyramidal plane, which also contains the closed back direction. It's because of this distortion of the C upon A ratio. So beta titanium, although it doesn't have, alpha titanium, although it doesn't have the same ductility as a cubic material, it does have, you can deform it. So this is called the alpha phase, the closed back hexagonal structure. Everybody happy with that? So we have sufficient numbers of slip systems for the polycrystalline material to be ductile. Now as we heat the titanium, above 890 degrees centigrade, it becomes body-centered cubic. And this is an extremely ductile phase because we've got lots and lots of slip systems. So we have an allotropic transition. Unlike aluminium, we have an allotropic transition, which means that we can manipulate the microstructure by heat treatment. And that is a major advantage of titanium over aluminium. Now, a lot of titanium is used in the chemicals industry because of its corrosion resistance, and I'll explain that in a bit more detail. But for example, these are reactor vessels, and they may not be completely made out of titanium. You might make them out of steel and then clad them with titanium so that the reaction actually happens in the titanium. The steel gives the supporting strength and structure to the chemical plant. And the titanium will be bonded to the steel by explosion bonding, for example. So you have a charge detonated which propagates, and solid state bonding of titanium to the steel. So a large quantity of titanium is used in the chemicals industry. Okay, this is another example of chemical plant with explosion clad titanium. Now, let me explain to you why titanium has a good corrosion resistance. This is a plot of the corrosion potential versus the corrosion current density. And you can think about this as a plot of free energy versus the rate of reaction. Yeah, because you know that electrochemical potential, if you multiply by ZF, then that becomes the free energy. Yeah? And current density is simply the rate at which a reaction happens. Right? So supposing I take a titanium, then for corrosion to happen, you have to have an anodic site where the metal is dissolving, and a cathodic site where you might have hydrogen evolution or oxygen reaction going on. Okay. Does this ring a bell? Okay. So you need two. You need anodic and cathodic sites. At the anodic site, if you're putting titanium in acid, then we will get the evolution of hydrogen. Okay. So this is the rate at which hydrogen evolves as I alter my electrochemical potential. And just focus on this line for the moment. What determines the steepness of that line? So as I increase my driving force, that means the difference between this and this, I get an increase in the hydrogen evolution rate. But what determines the slope of this line? So think about reactions in general. Okay, you provide a driving force, and even if it is a tiny driving force, why doesn't the reaction occur at an infinite rate? Yeah, and precisely. So there's a barrier to the evolution of hydrogen. Okay? And the bigger that barrier is, the steeper will be the slope. Okay? Now, on the anodic side, this is a typical form of curve for the dissolution of something that is passive. That means it forms a passive oxide film at a sufficiently large potential. So at first there's a very large reaction rate, but then it drops and we get a very small reaction rate because we formed an oxide film on the surface. Now of course the anodic and cathodic reactions must be balanced, mustn't they? You can't have current is going from anode to cathode, so clearly they must be balanced. So this is the net corrosion rate for pure titanium, where the current densities are balanced. Everyone happy with that? Now that's too high, and we're not taking advantage of the fact that we can form a passive oxide film on the surface. So in order to stimulate this crossover to happen in this region, we need to reduce the slope of this hydrogen evolution. So if we add a small amount of palladium or platinum to titanium, then you know that hydrogen evolution on platinum or palladium is very easy, and that's why we often use those as reference factors in chemical reactions. Then this line suddenly becomes that slope, and the intersection happens in the passive region, and you've greatly reduced the corrosion current. Okay, so you add a few percent of palladium or platinum to the titanium that is used in chemical plant, and you take advantage of this passive film, greatly reduce the corrosion current. Okay. Of course it's expensive, but it doesn't matter, you can recycle the stuff. Now, these are the typical sorts of phase diagrams for titanium alloys, and they have some obvious labels. This kind of a phase diagram is when we add solute, you increase the extent of the alpha or hexagonal closed packed phase field. Okay, so elements which do that, for example aluminium, are known as the alpha stabilizing elements. So one good way of remembering which elements stabilize alpha and which elements stabilize beta is as follows, that alpha is hexagonal closed packed, beta is body centered cubic. Solutes which are closed packed, for example aluminium, will stabilize beta. I got that wrong. No, that's right. So aluminium will stabilize alpha, whereas solids which are body centered cubic, for example molybdenum, will stabilize the beta phase. That's just a rule of the thumb way of remembering which elements should stabilize which phase. Here, when we add a solute, for example aluminium to titanium alloys, we increase the extent of the beta phase field, and therefore they are known as beta stabilizers. Now, we can also get eutectoid reactions. So here, for example, is a eutectoid reaction. Supposing I alloy with copper, I can get a eutectoid reaction. Eutectoid means a reaction happening in the solid state, right? And these reactions are incredibly slow in titanium. Any ideas why? You know, pearlite in steel I can form at a really low temperature if I want to, and it forms very rapidly. Exactly. So in the case of pearlite in steel, it's carbon that is diffusing to form the eutectoid. But here, you know, we would have substitutional elements diffusing to give us the eutectoid reaction. So very frequently, even though this is a eutectoid phase diagram, we don't actually get a eutectoid, and the whole phase diagram behaves as if it is like this. Okay? So you can suppress the eutectoid reaction even at relatively slow cooling rates, because it requires the diffusion of substitutional atoms. Now, titanium does dissolve a very large quantity of elements, and there are some very simple rules as to whether the elements dissolve substitutionally or interstitially, and these come from the work of Hume Rothery in Oxford back in the 1950s, where, you know, if the radius of the atom is about less than 0.6 of the host atom, then the elements dissolve interstitially. So all of these elements dissolve interstitially because the radius is much less than that of titanium, less than about 0.6. And if the radius is between 0.85 and 0.15, then they dissolve substitutionally. So large atoms basically dissolve substitutionally, small atoms dissolve interstitially. There's no need for you to remember which elements. Yeah, I'm just giving you an indication of, if you want substantial solubility, then you will get interstitial solution when the atoms are less than 0.6 of the host atom, and substitutional solution when it's between 0.85 and 1.15 of the radius of titanium. And beyond that, there's very limited solubility. This applies to any alloy system, not just to titanium. So, the most important elements are listed on this slide, remembering that elements like these, which are close-packed, will stabilize the hexagonal close-packed phase of titanium, and elements like these, which are body-centered cubic in crystal structure, will stabilize the body-centered cubic phase of titanium. And these particular elements, they do stabilize beta, but they can also form a eutectoid. So here we might have one of the phases being Ti, a compound of titanium and copper, forming with the beta as a eutectoid. Okay. One of the elements that is very important for titanium is hydrogen, because there is a huge solubility of hydrogen in titanium. And if you look at the dissolution of hydrogen into its atomic state in titanium, or indeed in any other metal, then you can express the free energy change as a standard free energy change plus RT log the activity of hydrogen inside your material and the partial pressure of gaseous hydrogen. Yeah? Are you familiar with this? You know, you remember the Allingham diagrams? So this is just an expression for the free energy change when you dissolve hydrogen inside the metal. And to find the equilibrium, I set this to 0, and therefore I have an expression for the activity of hydrogen in your metal as a function of pressure. And we will have this constant term and this term which varies with temperature. And the peculiar thing about titanium is that delta H is negative. So the enthalpy of solution is negative. In other words, the hydrogen wants to dissolve in titanium. And titanium can absorb a very large quantity of hydrogen reversibly. Reversibly means I can also get it out by heating it in a vacuum, for example. Now that could be useful because it's a mechanism for storing hydrogen in the solid state. So you absorb hydrogen into titanium and then you release it and use it as a fuel source. The other characteristic is that hydrogen solubility actually decreases as you raise temperature because of the sign of delta H. Now that means that we can use it potentially to contain for construction of the fusion reactor where there's a lot of hydrogen around. So at high temperatures, titanium is not embrittled by hydrogen because the solubility decreases at high temperatures.
What sort of, when you say decreases by how much, I mean?
Yeah.
Hydrogen still is very good at getting through.
It's very good. Unfortunately, I haven't got a scale here, okay? Yeah. But I can find out for you.
Yeah. At the higher temperatures, titanium is supposed to best for.
Yes. Now, one of the difficulties is that when hydrogen enters titanium, it forms a hydride. So here is an example of the hydride. And that hydride is associated with a very large volume change of the order of 20% volume change. So that severely embrittles the titanium. Now, of course, if you're using it for fuel storage, then that's not very important. But if it is in a structural application and you get hydride formation, that is very important because it will be severely embrittled. And it's not just titanium which does this. Zirconium, for example, also forms these hydrides. with a very large volume expansion. So it's an important problem. This is the reversible reaction for the storage of hydrogen. You form titanium hydrides, which are richer in hydrogen by adding hydrogen, and then you can reverse this reaction to release the hydrogen. Unfortunately, the energy density is only about 1/10 of that you get in lead-acid batteries at the moment. But here is an example of the hydrogen storage devices that are. This is a titanium-based hydrogen storage device, okay? And here it is in a toy car. So things are happening, but the density of energy storage is still much smaller than that of a lead-acid battery. These pictures I took just last year. Yeah.
So obviously, once it changes from it forms these hydrides. Once the reaction goes back through the way, the material is not the same as it was initially.
Yeah.
Cracks and
Yeah,
stuff.
absolutely. But it doesn't matter if it's not a structural application.
But I mean, when you then do it again, because it's got all the cracks and everything, can it hold the same amount of hydrogen, or is it slightly?
I mean, in principle, you want it in a finely divided state anyway, so that the reactions can happen. So it's not important in this application. Okay, let's now look at some specific alloys, and we'll start with alpha alloys. Remembering that alpha has the hexagonal closed-packed structure, and there is an empirical equation that is used in industry. All of these elements stabilize the alpha phase, and this equation is empirical. I don't expect you to remember it, but it indicates the potency of different elements in stabilizing alpha. You notice that oxygen is really potent in stabilizing the alpha phase. Okay? And one of the problems with aircraft alloys is that if you accidentally introduce oxygen into the alloy, you will end up with very hard alpha particles, which cause major problems with respect to fatigue failure. Okay? So for aircraft alloys, you want to keep the oxygen concentration down as low as possible. One of the major alpha alloys has this composition. All of these elements are simply there to solid solution strengthen. But alpha is hexagonal close-packed, and it does have ductility, but it's not sufficient ductility for forming into the components that we want to form. So we add a concentration of molybdenum, which stabilizes a small amount of beta phase at the temperature at which you are going to form the material. Okay, so this is simply added to add a small amount of beta phase into the microstructure to enhance the ductility of the majority alpha alloy. This is by far the most important alloy of titanium. Okay, it counts for the vast majority of titanium alloys marketed. It's a very simple alloy, titanium with 6 weight % of aluminium and 4 weight % of vanadium. And aluminium, of course, has a lower density than titanium, so adding aluminium reduces the density, and aluminium stabilizes the alpha phase, whereas vanadium stabilizes the beta phase. So we have a microstructure which is almost an equal mixture of alpha and beta. So this alloy tends to be really quite strong, of the order of 1100 megapascals, and it can even resist creep at reasonable temperatures where we put it into an aircraft engine or other applications. So this is the alloy that we will come across most frequently when we are discussing titanium. Now, of course, the body-centered cubic phase, that is the beta phase, has a ductile brittle transition. Okay? Have you come across a ductile brittle transition before? Yeah. So let me just quickly explain to you why you get a ductile brittle transition in body-centered cubic metals generally, and not in cubic closed pack metals, although that is only a general rule. Okay? So if I'm plotting the strength versus temperature, a body-centered cubic metal is rather loosely packed. So it's difficult for a dislocation to go from one equilibrium position to another. Okay? Because imagine that we have atoms which are further apart, then the next layer sinks into that layer, doesn't it? And therefore to slip is difficult, whereas if they are close packed, then the depth to which the next layer is sunk into the lower layer is less. So it's easier to slip. So the flow stress is extremely temperature dependent. Okay, so this is the flow stress in a body-centered cubic metal. On the other hand, the cleavage stress, that means to rip the atoms apart, is temperature insensitive. And therefore, above this temperature, you have ductile deformation, and below this temperature, you have brittle failure. So the fact that we have quite a lot of body-centered cubic phase in this alloy, and the fact that it is very strong, unfortunately means that its ductile brittle transition temperature is above room temperature, so when it fails in a brittle manner. Without much ductility. If I drew the corresponding flow stress for, say, austenite, which is phase-centered cubic, it would always be less than the cleavage stress. And that's why you don't get a ductile brittle transition in nickel or iron, which is FCC. Okay, I'll move on. So this is the typical microstructure of a Ti64 alloy, a mixture of alpha and beta. Beta is the stable phase at high temperature, and when you cool it, you precipitate these plates of alpha, and this is a higher magnification image. So you can see where it gets its strength from. It's a very fine microstructure, mixture of two phases, and therefore the strength is of the order of 1100 megapascals. Very, very nice alloy. Here are some more applications of titanium. These are valves for car engines, and you know that the valves have to move very quickly. Okay? So the lower the mass, the better the response. So if you make them out of light alloys, then that's even better. Unfortunately, these are expensive objects. Okay? So we need greatly to reduce the price of titanium, and hopefully the work in this department will lead to a reduction in the price. Okay? There are many, many applications which could open up if we could get cheaper titanium. Now, supposing that I wanted to stop titanium from burning easily, what would you do? What would you add? Chromium. Yeah, very good. Because chromium forms a very strong oxide. Okay, so here is a very large chromium addition, and we don't understand why, but just a binary titanium chromium alloy doesn't work in forming this oxide film. Okay? We need to add this large quantity of vanadium as well. Okay, so don't ask me why, but that's how it works. And alloys of this kind can be used up to 500 degrees centigrade. And there is another system which has been invented in Birmingham University. This alloy suffers from brittleness. Okay? There's another system which has been invented in Birmingham University, again based on chromium additions, but with certain impurities, very carefully controlled, so that you get a very high ductility. And that probably is going to have an impact on engine design in the near future. Okay, we have the beta phase stable at high temperatures, is body-centered cubic, and the alpha phase, which is hexagonal closed pack. And of course, if I cool slowly, from the beta phase field, I can precipitate alpha, and that will involve the diffusion of elements, because look, the alpha and beta have different equilibrium compositions. But I could also cool extremely rapidly, and then what do you expect will happen? Martensitic transformation, because Martensitic transformation does not require diffusion. Now, the Martensitic transformation begins at when we undercool below this temperature, and this is known as the Martensite start temperature, MS, the Martensite start temperature. Any idea why we have to supercool before we get Martensite? Sorry, please louder. I just need it seconds. It's a non-equilibrium phase. First of all, we are not allowing elements to partition. Okay? So you're trapping elements which really don't want to be there. Okay? Secondly, Martensitic transformation is associated with a lot of strain, because you're deforming the pattern in which the atoms are arranged, and therefore the overall shape of your crystal must change, and that shape has to be accommodated with the surroundings. So you have a lot of strain energy. But this is the reason why this line is not parallel to this, it's actually suppressed. So Martensitic transformation happens at a lower temperature than equilibrium transformation. So there's no problem in getting Martensitic alloys as well. There is one very peculiar transformation. Okay, let me just show you first of all the microstructure of martensite in form of thin plates, and we'll understand why martensite forms as thin plates in the next set of lectures, where we'll look at the mechanisms of martensitic transformations in general. And the plane on which the martensite forms is known as the Habit plane, and this just happens to be a strange plane which is close to 334 beta. Okay, at the moment we don't understand why, but you will after the next two lectures. And there's a particular orientation relationship between the parent and product phases. So you can see that the closed back plane of the body centered cubic structure and the closed back plane of the hexagonal martensite. And this is the closed back direction within that closed back plane. This actually isn't completely closed back. It's the closest back plane you can find in a body centered cubic. A body centered cubic lattice has no closed back planes, but this is the closest back plane. This is the closed back direction within that plane, and this is the closed back direction within that plane. And when we talk about martensite, you find that this is generally true, that the closest back planes tend to be parallel, and the closed back directions within those planes also tend to be parallel. So this is the martensite. But there is another very peculiar diffusionless transformation that is almost unique to titanium. It does happen in other systems, but it's of the biggest importance in titanium. So imagine that these are our planes of atoms. Okay, so the 1-1-1 planes. And you know that the 1-1-1 planes are stacked in ABC sequence, right? What happens is that you effectively get a displacement wave going through the system, so that these two planes coalesce. You double the atomic density in that plane. Okay? So you end up with an AB dashed, AB dashed, AB dashed sequence with alternate layers having double the atomic density. So you can imagine that's a very strange transformation where you take the 1-1-1 planes of beta, which are stacked in ABC sequence, and a pair of those planes collapses to give you an AB dashed, AB dash, B dash, because it's now got double the atomic density. And you can see why I'm using a displacement wave, because here this is being pushed in that direction, and this is being pushed in that direction, and that's at a node, so there's nothing happening there. Okay? So you can describe it in terms of a displacement wave. Yeah?
How do you get rid of density? Surely
Yeah?
you've got all the atoms in nice order structure. How do you fit any more in?
Push it together. You know, the only way I can answer how is that there is a reduction in free energy when this happens.
So the volume decreases.
No, this is the problem. You see, this phase severely embrittles the titanium. So this is called the beta to omega transition. Yeah? it has the most peculiar C/A ratio, which is far less than 1. Okay, far less than 1. So if you like AB dash is like a hexagonal. Yeah? With a C/A ratio which I'm recalling from memory is about 0.6, it's in your notes. So it severely embrittles the titanium. And it's, of course, it's a diffusionless transformation. Now, because of all the strains that this causes, your diffraction pattern becomes streaked. In other words, strain is reflected in changes in lattice parameter, right? If I elastically strain the lattice, you are effectively changing the spacing. And remember that in an electron diffraction pattern, the distance between these spots is related to 1 upon the spacing of those planes. So if I'm causing a variation in the spacing, then I will see streaks in the electron diffraction pattern in this direction. So if you're observing this transformation happening in a transmission electron microscope, you will observe streaking of the pattern, diffuse streaking of the pattern. Okay, to finish off, there is an important class of alloys which are precipitation hardened alloys. So obviously, if you have a phase diagram which shows this kind of miscibility, solubility change, then you can age harden it by heat treating here, quenching, and allowing precipitation to happen. And the most popular alloy for this kind of heat treatment is the titanium copper system. So this is a popular alloy in which you precipitate Ti2Cu. You can see the Ti2Cu. And these dark regions that you see are strain fields. Yeah, this is a transmission electron micrograph, and if you have strain, then you'll get diffraction effects. So these coherency strains, they harden the material. So this is a precipitation hardened alloy. Now finally, a few years ago there was a huge interest in making intermetallic compounds with titanium. So for example, okay, this is just the titanium copper precipitation hardened component. We can make titanium aluminides, TiAl or TiAl3, and of course they have the big advantage of low density and oxidation resistance. But like many intermetallic compounds, they're not particularly ductile, okay, and that's the reason why they haven't been as successful as they might have been. But there are certain applications where their oxidation resistance, because they have a large concentration of aluminium, is very important. And this is a turbocharger. They rotate at a very, very high RPM. I forget the numbers, but it's of the order of 10,000 RPM. Okay. So in a powerful car, you want to boost the power, then you have something known as a turbocharger. And this one is made out of titanium aluminide, very low density. And if you compare that with the previous technology, then they were made out of nickel-based superalloys, which has a much higher density of the order of 8 grams per centimeter cube. So there are some applications of titanium aluminides which are now, industrially important and already find applications in very expensive cars. But in general, because of their lack of ductility, they haven't lived up to the promise just 5 or 10 years ago. Okay, so that finishes titanium alloys, and the next 2 lectures I will deal with martensitic transformations. Do you have any questions?
In the beta to omega transformation, the little white spots that were shown in the micrograph, are these voids?
No, those were the actual omega phase. So it looks like precipitates, doesn't it? But these are the omega phase particles. You had a question?
Yeah, I'm still not sure I understand how that works, how the
Right.
beta to omega transformation.
So look, we have these planes of atoms, which are the 1-1-1 planes, and they're stacked in a repeat sequence A, B, C, A, B, C, and they all have the same numbers of atoms per unit area. Okay? Now imagine that I pass a displacement wave through the system, okay, where this represents the magnitude of the displacement. Okay? This A plane is located at the nodes, so it's not affected by the displacement wave. The B plane will be displaced in this direction, and this will be displaced in the opposite direction because it's a negative displacement. So that causes the B and C planes to collapse.
There's no overall volume change.
There is a volume change, a large volume change.
So overall, from beta to omega,
Yes.
it's if you have chunk metal, it shrink.
Well, the phase fraction is quite small. Okay, you can see the amount of omega that we formed is quite small. It's not the whole of it that transforms into omega. Small regions.
You say this like displacement wave going through. What is the driving force for this
Yeah.
transformation?
I mean, the displacement wave is just a way of thinking about it.
Yeah.
But the driving force is that we have added so much alloying element, okay, that we are somewhere in this region, and the beta doesn't want to stay as beta. You know, it's not a stable phase.
But it can't change.
No. So simply that we have supercooled it sufficiently to stimulate this particular transformation. It's not an equilibrium phase.
Would it be possible to make the entire material
Question.
change?
Yeah.
Because then you surely can have a really good reversible.
It's a good question. I don't know is the answer, but it's a very good question to think about.
So does that, just sorry, again, I'm trying to imagine the idea of trying to fit that many atoms in.
Yeah.
Does that initiate a large amount of stress in
Yeah.
that single planes?
It does, and this is the reason why we get a peculiar C upon A ratio, and also why we embrittle the material when the omega phase forms. Okay, good.